So the first question I'm going to go through is finding the domain of the square root of 2x minus x cubed. So to start this question, let's actually take a look at the right-hand side where I've reproduced the graph of what this would look like if you were to input this function into a graphing software. So to understand this graph, where you can see that the domain actually ceases to exist at one period of time, let's first look at the math behind this original function. So if you were to simplify this, you would start by first isolating the x that exists in both of these terms in the equation. So you can have x times the quantity of 2 minus x squared. You can simplify this term further, so you can make that equal to x times the quantity of square root of 2 minus x and the square root of 2 plus x. These are two separate quantities. So for all three of these terms, you can come to a conclusion that there are points where this domain is equal to 0. So those zeros actually are 0, positive square root of 2, and negative square root of 2. So then the question is, why are these points important? So if you're to actually look at these three values and compare them to the graph, they're actually where the identity of the function changes, where sometimes the domain exists and then it ceases to exist after one of these zeros, or it begins to exist again at a 0 and ceases to exist once more after a 0. So to understand this concept, you have to actually look at the concept of a square root and a domain in general. So domain is simply anywhere where the function can actually have a real value. So with square roots, for example, when can a square root have a non-real value? What makes this thing different from something like y equals x? So if y equals x, let me just write that up here, y is equal to x. If you were to draw that as function, you would just have a straight line going through some kind of going through the Cartesian plane. Is there any place where y equals x cannot exist? No, it's an infinitely bound value. But the thing is, with square roots, there are points where they can exist, and that's where the square root is negative. So when you have, I'll draw that right here on the bottom. Let's see, you have the square root of negative 1. What does that really turn into? That equals I. That's an imaginary number. That means there is no value associated with it. So if you have a domain that's equal to I, that's not a domain. That's where you can find these discontinuities existing. So the question that most people who would reflect upon this would ask is, how do you know when you're going past one of these zeros that either A, the domain will discontinue, or B, the domain will begin, or C, it will discontinue once more, as you can see in this graph right here. So to understand that, let's actually consider all of these zeros along a number line. So one technique that I came up with over time is to actually plot each and every one of the terms, and I should include this in the picture first. So each and every one of these terms under the square root along the number line and test values along it. So you can see that where I've drawn a V is where at least one of these is equal to a 0. So for example, I have a negative square root of 2, negative square root of 2. You have a negative value at y equals x. You have a positive value at y equals square root of 2 minus x. But then you have a 0 where it's square root of 2 plus x. So each and every one of these values I've labeled as a v actually is one of those points where you get a 0 somewhere along the line. So before and after those points, you can test any value in the whole entire world. And you can, instead of actually looking for a specific value, you can just look for whether the sign is positive or negative. If it's positive, that means the domain exists because a square root of a positive number has a real domain. But if the value is negative, if the value of product of all of these is negative, that means there's an imaginary domain. So that means the domain does not exist there and it's not real. So in my example, I've tested x, square root of 2 minus x, and square root of 2 plus x. And along each of these, I would multiply the signs. So I pretend that all of these are like negative 1, positive 1, I'll write it out, negative 1, positive 1, negative 1. It does not have to be negative 1 or positive 1. This is just for an example. I shouldn't get rid of that so you don't get confused. So if you have a negative number and you multiply it by a negative number, you get a positive number. You multiply that positive number by another positive number and you get a positive value. With this situation, you have a 0, so it's automatically going to carry down to make a 0 as the product. When you have negative 1 coming into these different terms, negative 1 times x is going to be negative 1. A negative 1, when you plug that into this term, square root of 2 minus x, because this is a negative and that's a negative, it becomes square root of 2 plus 1, which is a positive number. When you have square root of 2 plus x and you input the negative 1 into it, square root of 2 will always be larger than any value that can fit in between these two. So you could have negative 0.11111, and that's still going to be smaller than this guy. So it's not going to make it negative enough that it actually crosses beyond 0. That means this value will always be positive. So you can always assume that this is going to have a positive value. So that's negative times a positive, which comes with a negative value. With x equals 0, because there's a 0 from y equals x, this 0 carries down. Then next is where x equals 1. So if you plug in these values for x equals 1 into this equation, you can have positive values come across the whole entire way, which means the product of them will also be positive. With a square root of 2, once again, you'll have a 0 coming into the equation here, so it automatically becomes a 0. And then everything beyond square root of 2 can be tested by using the value of 2. So if I was to plug in 2, the problem is that even though y equals x would be positive, and y equals square root of 2 plus x is a positive value, this value right here becomes negative. So that continuously makes this into what? A negative value once you take the product of them. So in general, one thing you can always think is that real values only exist where the product is greater than or equal to 0. Because of what? Because of the fact that this is a square root function. So looking at my terms right here, we have the products that have positives and zeros and negatives as well. So one can conclude that everything, I'll say that this is from negative infinity and that's from positive infinity. So everything from negative infinity to a negative square root of 2, including that value, is going to have a domain, but everything between negative square root of 2 and 0 will not have a domain because of the fact that the product is negative. However, thereafter you can see that from between 0 and square root of 2, you get positive value, therefore the domain exists, and everything beyond square root of 2 until infinity has a negative value as the product, so the domain does not exist. So we can get from this, using these signs, that d is equal to values from negative infinity to the negative square root of 2, including that value, and then the union of that with values from 0 to 2, both including those values. If you take this answer and compare it to this graph as well, I'll rewrite the answer right here. So d is equal to negative square root of 2, and then 2, including, then union of 0 and 2. You can see that negative infinity to square root of 2, that's validated by this graph, because from negative infinity to square root of 2, you have real values. You can see that there's a gap between 2, this should be negative square root of 2, and that's positive square root of 2. So everything between negative square root of 2 and 0, there is no domain, therefore there are no values. And then once more, you can see that in this part, it's 0 to positive square root of 2, therefore there is an existing domain here, and beyond that point, you'll see that everything from square root of 2 into infinity will have no value, therefore it is non-existent. Which means that this method does prove that there is a domain between these values, and you can mathematically find whether or not there is actually a real value or imaginary value.